All right, let me just do a little example to calculate, to give you an intuition for the size of the RMS velocities in some gas molecules. So we calculated the statistical distribution, the Maxwell-Boltzmann distribution for velocities in the last lecture, and now I'm just going to apply it. So, like for example, for argon at 300 Kelvin. So if you look at argon has a molecular weight of 39.9 if you go to the periodic table, and that's in atomic mass units. So if I turn that into grams, I would have to multiply by the weight of a neutron. And that'll give me 66.6 e to the minus 27 kilograms for a single molecule. And then I would calculate the RMS velocity as 3 times kBt over m, which comes out to be 431 meters a second. So that's pretty fast, but not all that fast compared to some other things. Like you'll see that sound waves in solid materials typically travel at several thousand meters a second at room temperature. So this is a lower speed than that. And as a side note, let me just make a little side note here. So how fast is that compared to the speed of sound in a gas? Well, it turns out that the speed of sound in a gas so I won't derive this, but if you take a fluid mechanics course, it turns out that the exact formula for the speed of sound in a gas is square root of gamma, where gamma is the ratio of heat capacity, let's see if I can do this right. It's the ratio of the enthalpy-based, or the constant pressure heat capacity to the constant volume heat capacity, which for most gases is about 1.4. Basically, like the formula for the speed of sound that you would get from continuum mechanics, like fluid mechanics, is pretty similar, like the same order of magnitude at least. And so, basically they're off by like a small factor. Anyway, so like the sound speed for argon turns out to be 308 meters a second. So the RMS speed is actually quite similar. Okay. So that's just for argon. They're definitely related quantities. They only differ by a small numerical constant. Okay, I'm not going to write it all out for all of the other materials, but I'll just give you some examples. So, like, what's the only thing that changes when you change to different gases is the molecular weight, right? So, just stop for a second and think about, what molecule has the highest RMS speed? Like, what molecules travel the fastest? I'll give you a second to think. All right, time's up. So basically the only thing that affects the speed of a molecule is basically what mass the molecule is and what temperature you are interested in. So at room temperature, the only thing that matters is the mass of the gas. So the things that move the fastest are going to be things that are light. Things that have a small m will have a high v. So those would be things like hydrogen, right? So hydrogen has a molecular weight of 2, and the associated RMS speed is about 1900 meters a second. Helium, so that's m equal 4 most of the time. That would be 1300. So remember, it goes as the square root, so it doesn't change that much when you change things. So even though I doubled things, it didn't really cut the sound speed in half. Probably the other most interesting thing is nitrogen. So most of air is nitrogen. So that's m equal 28. That'll give you a VRMS of 515. Oxygen's almost the same. I think oxygen is 16, has a molecular weight of 16. Oh, I guess. Wait, what happened here? Molecular weight. Oh, it's because it's oxygen. It's 2 oxygens, right? So 32 for oxygen would give you about the same number. And then, like, let me give you a really heavy example. So, like, what's the slowest you could ever really make the RMS speed? Well, I guess xenon's probably the heaviest gas I could think of. Maybe radon if you're really adventurous. So that's 131, and that'll give you a VRMS of about 238 meters a second. So basically, like, this is the whole range of possibilities. At room temperature, anyway. If you want to get up to super high speeds, you can, of course, go to super high temperatures, but remember, it's a square root behavior. And so, if you go up by, if I double the absolute temperature, I only increase the speed by a factor of, 1.4. So anyway, so those are some typical calculations.